Hello, everyone. So in this part, we're going to go through the parts of homework 4, part 2. We're going to start with some theory about sequence, attention, and the LAS paper, and some ideas about what we needed to implement. Stuart is going to take you over the remaining parts and the starter notebook. So by now, you should be very familiar with this architecture, with this problem formulation, which is encoder-decoder, where you have your input coming in here to the encoder. You create some sort of representation of it, and then you will pass only that representation to your decoder, which will then create your outputs, which is here your wise predictions. So in our case, for this homework, we're trying to predict from voices, from sounds, from speech data. We're trying to predict the transcriptions for them. So in a vanilla way, or in a vanilla sequence, you will have your inputs coming in like this. You create your hidden states by passing them through a couple of LSTM layers. Then all these hidden states will be put into your decoder. From here, it's going to go through your decoder. The issue about this is that we have a bottleneck here of some sort, because every piece of information going is going to be just concatenated into only this weight vector or only this one connection, which makes it hard for our decoder to recognize and understand where each of these output corresponds to each of these inputs. Because in some languages, for example, if you want to talk about a translation formulation, you might have an input in German and an output in English. And the input in German might have a different sequence or a different ordering of words. So for example, Y3 might be related to this one. And it happens once and again that the first and last pieces of information or tokens are related in these languages. So you want something that will show you how each part of the input is related to each part of the output. And this is where attention comes into play. Attention basically is a way of taking your input, transform it into hidden layers, which happens always, but then the attention here tells the decoder where to focus or where to pay attention, if you might say, in the input. So you have your hidden layers, and then each part of each hidden layer is passed to each input of the decoder at the same time. And then each decoder part will recognize and will then decide which part of the input to focus on, depending on the weight of these connections. So to put this more concretely, we have a hidden vector here, and we have a weight vector here, alpha, and you have a context vector that is then added to your input, to your decoder. So what will happen is that you will multiply these weights with your hidden vectors, and that's what we call a context vector that is then concatenated or added in some way to your input, to your decoder. So if you want to look into more details into this, you can refer as well to the attention and transformers lectures early in the semester. But you have your hidden layer, your hidden inputs, your hidden outputs, I mean, and then you get both your key and value vectors from them using some weights or some transformation. And then you would use these key and values to do some transformation to the output of your LSTM cells, or to some form of output that you want your input to be transformed into. So looking into this more concretely here, we see that our key and values are taken. They are then input into a sort of transformation here that will give you your context vector, which will then be added to your input, which will go then to what we call a CDN, or a character decoding network. Then this will be then taken from here, from your output, both of them, both your Y value, which is the predicted output, and your context that we just calculated, the two of them will be used as input to our next time step. So this way we can use the previous prediction as a way to predict what will happen next. There are a few ways that you can calculate your context vectors. One of them is cosine similarity vector, which cosine similarity attention, which will take a cosine similarity between the query and your key, and then it will use that as a way to weight your value vectors, and then those are what will then be accounted as context vectors, which will then be concatenated with your output, with your Ys. Or another option is to use a scaled dot product attention, which is this is what you will see. We want you to start with in the homework, where you will multiply your query and you will multiply that with your keys. You will then divide by the length of your keys and pass it through a softmax. So passing it by a softmax is a way to making it into probabilities and into actual weights, which then you will multiply it by your value. This will act as a way to weight or to act as value weights to make sure that your values don't blow up or blow down, because a softmax will put everything into a neat 0 and 1 range. So this then will be concatenated as we described to your Ys and will be used for your final prediction layer. So if we want to take a look at the entire system, how it would look like, an entire attention-based sequence model, we will have first our encoder, which will take our input and will create hidden representations or embeddings for that. And this is E. Then we will have our attention layer or attention calculations, which will take our hidden vectors, and then it will transpose them and give us our attention weights and context vectors. And then at the end, we have our decoder, which will take both the attention and the hidden values, as well as the previous time step input or the previous time step output, and it will give us our predicted output at the end. So this is the general formulation of our encoder decoder attention-based model or sequence attention. We will look into one way of doing this, which is called an LAS. So LAS stands for listen, attend, and spell, which is corresponding to the three parts of our encoder decoder architecture. So the listener is the way to transform our input into hidden representation, which is the encoder. Attention is the same thing, and then the spell is the decoder part, which will take our transformed inputs and then will give us our expected output predictions and sequences. So there is a problem that comes with trying to predict from longer sequences of input. You're trying to predict some shorter output sequences. For example, an input speech vector might contain around, let's say, 100 vectors per second, but then a person normally talks at a rate of 3 words per second, or in characters, that's around 12 to 15 characters per second. So how do you address this? There is a way that the Liss paper proposed, which will help in this formulation. So if you look at the normal LSTM or bidirectional LSTM model, you would see that the length of the input, if this is 1000, our output will be also the same. It will be 1000 as well. So there is no shrinking of the input length happening here. This will make our model very big, because the way it's like there is no compression happening or no sampling happening here. Alternatively, we would use something that's called a pyramidal bidirectional LSTM. So the idea is that we have a pyramid of an LSTM that will concatenate or reduce the input length as we're going through the layers, and this will allow us to have better performance with kind of smaller models that will retrieve information in a much more efficient way. So if we look at what happens here, we first will have our base LSTM, which will take the input as is and will give us the output as is. But here, something interesting happens that we concatenate each two adjacent inputs into one. So if we have a vector that is of this shape, so the output here, let's call them x1, x2, x3, etc. What will happen is that we'll concatenate these two, x1 and x2, we'll make them into one vector, and we'll do the same all the way throughout the entire thing. So this way, the shape of our vector is going to stay the same because we have the same elements, but we're going to have a sequence length over 2, because we now have cut half of the dimensions that we have. So this will allow us to use a smaller LSTM in the next step. So by this will allow us to have this effect. Well, here we'll have t. In the next layer, we'll have t over 2. In the next layer, we'll have t over 4. And in the next layer, we'll have t over 8, and going through that. So this is what the Liss paper proposes, that we go up until a t over 8 compression, which means that we're going to use a base LSTM and then 3 layers of three pyramids, which will take our input and compress it all the way to an eighth of its original input size. So how do you deal with the concatenated with the combined input? So we said that we're going to have an x1 and an x2. So one thing that you can do is you can just concatenate them together, or you can get the mean out of them. So basically, you can start with concatenating, and then you can try taking the mean, which will also compress information a bit more. But so this is also a test that you can try out. Baseline starts with you just concatenating the inputs, but then you can also try the other ways of building a pyramidal LSTM. Moving forward, so this is how the Liss paper looks like. Generally, you have a pyramidal LSTM, and then you have your attention, which is dot product attention, and here you have your output creating decoder or speller. So one thing that's interesting about the way that this problem is formalized, that we don't use a normal LSTM for our decoder. So everything that we've been talking about until now, attention, as we described, and this PPLSTM, this is in the encoder. This is the L part, and this is A. So if you want to talk about the S part, about the speller, so one thing that we can see is that in the speller, we can't go using the same ideas that we use in our HW4 part 2, which we just use normal LSTM layers. The issue with this is that we don't know what the output length is. So we don't know how long this Y vector is going to be. We just continue until we hit an end of sentence token, which is something that's not natural to the text, but it's similar to the SOS token, which we used previously to initialize our decoder. So you start with an SOS, and then you start with a zero context vector, and then you will start your decoder part. So these two are not natural to our decode speech, but then we use them as a way to indicate that we want to start the decoding, or we have reached an end of sentence, in this case an end of sequence, and then this is what the model predicted sequence was. So since we don't know how long this is, we can't use a normal LSTM. Instead, we would use something called an LSTM cell, which is this one, and we're going to stack them together in layers. Then the LSTM cell is basically the basic building block of a PyTorch LSTM layer. So instead of us having to build all these and then we know what the input is, because normally you know what the input is and you just pass it all together as once in our previous homeworks. Here you will use the cell, which is the basic building block. You will build as many cells as you want. This is not a cell, but you can build up to whatever cell that you want, depending on your choice of design. LAS starts with only 2 cells, but then you can change it, of course. And then you do a for loop until you hit an EOS token. So you're gonna take the output of your previous layer, and you take your context vector that you just calculated from attention, and then you're gonna for loop it through the next layer, and you're gonna go there until you finally decode the predicted end of sentence token. So this is another thing to pay attention to, is that you're not going to be using just Torch's LSTM layer. You're going to be using Torch's LSTM cell, which will give you a bit more to think about, but it's pretty simple. You just add a for loop and you just pass the output of the previous layer as input to the next layer. So this is basically it. So before we go into the other parts, so the baseline is LAS, but as always, what we need from you in this homework is to implement an attention-based sequence model. So you can start with the baseline of LAS, but then you can also work on implementing transformers, conformers, or any of the state-of-the-art models that you find that you think might give you great performance in this homework, because it's just an ASR. It's a speech transcription homework. The idea is that us as TAs, we have good experience with LAS, and we have some ideas that we want you to implement, like using an LSTM cell and like implementing a PPLSTM, and as well as the attention method that we described here. But you're free to try whatever you want. In the write-up, we have mentioned a couple other more ways of doing attention, multi-head attention. And on that note as well, you can write transformers, you can do that part on your own. One thing to note is that you will find less help or less assistance from the TAs with these implementations. You're going to have to go and find the papers, and then you're going to have to go and find some guidelines on how to write it. You're going to have to write everything on your own. You're not allowed as once again to just use one big implementation from PyTorch or one big piece of code you find online. You're going to have to write your own code, and so you're going to be kind of on your own on these parts. But again, you're free to try it whatever you want. So there are a few tips that might help you during training, because this is a bigger homework. Implementation is going to take a bit more time, but then also as well, getting to the desired cutoffs will take you as well some ideas that we would like you to look into. So the first idea is teacher forcing. So what teacher forcing is that, okay, so when a model starts, you will have some sort of hidden representation, which might not be the best, and then you'll have also some random weights that have been initialized here. All this will accumulate in you having probably a wrong expected output. So your output of the model might be wrong, and if you feed that output here, then the rest of the model is just gonna give you gibberish. It's gonna give you bad predictions for a sequence. So what you can do is instead of using this, you can use the actual labels while training. You can use the actual sequence, the code sequence while training as input to your next time step. So this might seem counterintuitive, but this will happen at the first part of training. You're gonna force your model to learn because you're giving it the correct predictions. But then you're not going to continue doing this, because this can teach your model to always predict that, okay, what I have gotten was correct. I'm going to just assume that this is correct and then decode based on that, because in actuality, this is why we have losses and we count on limit time distance, your first prediction might be wrong, but then you want your network to be able to predict everything else, regardless of this first prediction. So what you're going to do is you will start with giving the decoder network always the right prediction from the previous layer, but then you're gonna start slowly taking that away. So you have a T-shirt forcing probability that should start at 1. You run it at 1 for a while, which means that you're always giving it the correct prediction, but then you have to reduce that until you reach a certain point where you then stick on it. So this point is 0.7, but then you should start at 1. So the scheduling part here is up to you. How do you want to go about it? Do you want to just do like time intervals, each 3 or 5 epochs? You want to reduce the T-shirt forcing until you reach your 0.7, and then you stick there until the end of training? Or you want to do a more complex T-shirt forcing schedule? It's up to you, but we highly recommend you to use T-shirt forcing. The start of the implementation is already in the notebook, and you can look through the write-up. It has some pretty good ideas on how to do this. Another thing is that you might want to look into is gumball noise. So in our experiments, it gave less effect than other regularization and data augmentation techniques, but it's still worth looking into. So gumball noise is a way that you will add noise to your output predictions. So before you get your sequence, when you get your P's here, you want to add some noise there, because you want to again allow your model to predict correctly, although it started predicting incorrectly. So this way you're gonna force the model to predict incorrectly sometimes to allow it to predict correctly most of the times that it starts predicting incorrectly naturally. So look into it. The write-up also mentions where you can work on this. Yeah, but I recommend that you come to this last after you try everything else. Data augmentation, you can try time masking, frequency masking, and normalization. It's standard data techniques that they will give you a good boost in your limit time distance. And yeah, the final thing that we would want to look into is beam search, LSTM beam search, which is different again from the way that we did it in Homework 3. So just like we said here, when we proposed using an LSTM cell instead of an LSTM layer, because you don't know what the output length is, you want to continue predicting. You want to continue predicting until you hit an EOS symbol. LSTM beam is different than a normal CT3 beam in terms of that. Okay, let's say that we have a beam width of 3. You're going to take the top 3 predictions from this layer at this time step. You're going to take the top 3, which these are the top 3, and then you're going to pass each one of them through either your next layer, your next time step. You're going to create a brand new H's. You're going to calculate the context and then do everything, and then you're going to have let's say here 9 of them, 9 new predictions. You're going to pick only the best. Let's say this one, and this one. You're going to pick only the best 3, and then you're going to do the same again with them. You're going to again pass each one through a layer, a time step layer, and get 3, and then pick the best 3 until you hit an end of sentence for one of the paths, and then you're going to evaluate that path as the path that you want to predict as your correct path. This will allow you to not get stuck in the beginning, and it allow you to look further down the sequence. And the implementation is pretty straightforward here. So your decoded path is just a multiplication of your current predicted time, given that you have a previous hidden layer, a previous prediction, and a previous context. So it's just you're just going to predict depending on what the path that you have been through before, the last path that you have seen. And another idea is that if you just multiply these paths, because this is just chain rule, if you multiply the path probabilities, it can explode or vanish but then the trick that we do in probability is always to take the log, which will transform our products into summations, and summations are much nicer to work with. So you will just take the summation of the product, you take the summation of the logs of the probabilities of the entire path. So I here is time step. I goes until you find an end of sentence prediction. So that's it for my part. Start early with this homework. You have a few things to implement. You have to implement the pyramidal LSTM by LSTM. You have to work on implementing and getting the attention code and attention implementation ready and working correctly. You have some ideas that you need to look into in your LSTM cell implementation here in LAS. You need to also try and figure out how to do teacher forcing. But yeah, if you do these things, this should be okay, and you should be able to get through this homework with no problem. But once again, you should start early. And yeah, good luck. And I'll pass it on to Swati to go through the starter notebook.